In this video, I'm going to be describing the mechanisms of elimination reactions that involve alkyl halides. While most alkyl halides that we will be dealing with in class only have one leaving group, I will be going over the mechanisms of elimination reactions on alkyl halides that have two leaving groups. So instead of your final product having a molecule with an alkene in it, it will leave you with a molecule that has a triple bond or an alkyne. So for this example, our first molecule that we start off with has two bromide ions attached at the 2 position. Here we have a strong base, which is known as T-butoxide. So next we need to determine whether or not the reaction is going to be an E1 reaction or an E2 reaction. And ultimately this is going to be decided by the solvent. In order for a reaction to be an E2 reaction, it has to have a strong base. And we do, so this reaction does have potential to be an E1 or E2. Looking at the solvent, we can see that we have an ether. Because this ether is polar aprotic, it will not solvate the base. Therefore, the base will remain a strong base, and the reaction will be an E2 reaction. However, if we were to put water here instead of the ether, the water, being a weak base, would solvate the T-butoxide, and then the T-butoxide would become a weak base. Therefore, the reaction would have to be an E1, because E2 reactions have to have strong base. From this point, we want to locate the hydrogens, or the protons, that are located at the beta points compared to the bromides. So, ultimately, there's a hydrogen here. Actually, there's 3 hydrogens there. And on here, there's 2 hydrogens. Both positions are beta, but we do not want to use the protons that are on the end right here. You always want to use protons that are somewhere in the middle. So therefore, we're going to be using these 2 protons right here in the reaction. So the first step of a reaction is that this T-butoxide is going to deprotonate one of these hydrogens. Once this hydrogen is deprotonated, the electrons from this bond move over here, and they will form a double bond. However, the formation of this double bond will have to bump off these electrons, and these electrons will go onto the bromine, and the bromine ion will then be booted off. And that will leave you with this molecule. Now when writing the molecule, you won't actually write out the hydrogens that are on here, but I'm doing that just as a reference purpose. So from here, you have to pretty much repeat that step one more time in an effort to get rid of that second bromide ion. So from here, this hydrogen is going to be deprotonated, and then these 2 electrons are going to be moved right here, and that's going to form a triple bond. However, the triple bond here is going to bump off these 2 electrons that belong to the bromide, and they're going to be moved onto the bromide ion, and that bromide is going to be pushed off. So from there, you will end up with your final product that will look like this. So on this second example, we have a similar molecule, except instead of having 2 groups off of one, like that, we actually have a chloride group coming off of here, and a chlorine coming off of here. So now I'm going to put in our protons so that we have an idea of where those are. And again, like in the last example, you want to take a proton from a beta group. So the beta groups from this chlorine are going to be here. There's a proton, and there's also 3 protons there. But as I mentioned before, you do not want to take the protons off of the end group. You want to take them off of the group in the middle. And the same thing goes for this second chlorine. It's got hydrogen groups here, but it's also got a proton there. And we obviously want to take that one because it's in the middle. So just like the last reaction, this is also going to be an E2. And that is because this ether right here is polar aprotic, therefore it is not going to solvate this base, so that base is going to remain strong, making this reaction an E2. So our first step is to deprotonate. So this is going to deprotonate that proton, therefore these two electrons are going to get bumped right here in the middle. And another thing that I didn't mention before in the last example is whenever these protons are getting bumped because of the deprotonation, the bond will always go in the middle. It will not go on the side right there. And that's just because if it's in the middle, it provides better sterics. So once those two electrons were bumped into the middle, that is going to cause this chlorine, these two electrons with this chlorine, to get moved onto the chlorine ion, and then the chlorine is going to get bumped off. So that would in turn leave us with this molecule. So from this molecule, we know that we still have a proton right there. So now what happens is this comes and deprotonates this proton. These two electrons get bumped into the middle, and this newly formed triple bond in the middle in turn is going to bump these electrons onto the chlorine ion, and that chlorine ion is going to leave. Therefore, in the end, we end up with the same molecule that we had before in the first example, and it looks like that. So overall, the mechanisms for alkyl halides that have two leaving groups is really similar to mechanisms with alkyl halides that only have one leaving group. Basically, all you do is you just add on an extra step, and that extra step is pretty much just a repeat of the first step involving the deprotonation and then the forming of a pi bond and the booting off of one of the ions. The main difference is that if you only have one leaving group, your end result will have only a double bond or an alkene, whereas if you have two leaving groups, the final result has an alkyne or a triple bond.